A 2.30 kilogram mass hangs vertically at rest from a spring. If the spring displaces 15.4 centimeters, find the force constant. Well, let's draw a free body diagram. Here's our mass. We have a weight that acts on that mass equal to m times g. So this number, 22.56 newtons, was calculated by taking 2.30 kilograms times 9.81 meters per second squared. We also have a spring that is acting, holding the mass up, and there's an elastic force in the spring. By Hooke's law, that elastic force is numerically equal to k times delta x. Now, in the equation for Hooke's law, there is often a negative sign in front of the k. We've taken that into account by putting the force of the spring in the direction that we know it goes. We know it holds the mass up, so now we're not going to worry about the negative sign. So let's write a Newton's second law equation in this up and down direction. I'm going to choose up to be positive. K times delta x. Delta x is the amount of stretch in the spring, and notice that I've converted it from centimeters into meters. So k times delta x upward minus 22.56 downward, and by Newton's second law that should equal the mass of the object times the acceleration of the object. This object is at rest, so it has no acceleration, and we want to calculate the force constant, also called the spring constant. It's simply a matter of adding 22.56 to both sides, dividing both sides by 0.154 meters, and calculating the force constant or the spring constant as being 146 newtons per meter. An 8.4 kilogram mass is at rest on a horizontal surface. So we have a mass at rest on a horizontal surface. There's a rope that's tied to the mass. It has a certain tension, 73 newtons, and it's angled 43 degrees above horizontal. So you can see in my picture here, horizontal would be straight that way. So this angle is 43 degrees above horizontal. Also, a 58 Newton force presses the mass into the surface, and we want to find the normal force and the friction force. So let's draw a free body diagram, and we're going to use just numbers. There's the mass, 8.4 kilograms. Our weight is m times g. So 8.4 times 9.81 is 82.4 newtons. This tension, you can see in the picture, is acting in a direction that is neither parallel nor perpendicular to the surface. So I'm going to break it into its components. This green vector is going to be found by taking tension times cosine of 43. So that number will be this, 73 newtons times the cosine of 43. This black vector, pointing up, is going to be found by taking the tension, 73 newtons, times the sine of 43. We also have a 58 Newton force pressing the mass into the surface. We have a normal force. Now we don't know what the magnitude of that normal force is, but we know that it's going to be pointing up, and of course we have a static friction force, which we know will be in opposition to any sideways forces, so therefore we know it's going to point to the left. So let's sum the forces in the perpendicular to the surface direction. I'm going to choose up to be positive. 49.8 is up, normal force is up, but 58 is down, so it's negative, and 82.4 is down, so that's negative. And Newton's second law says that the sum of these forces should add up to the mass, 8.4 kilograms, times the acceleration perpendicular to the surface. Well, this mass is at rest, so the right side turns to 0, and you can see then that we should be able to solve this equation for the normal force, and it turns out to be, to two significant figures, 91 newtons. If we now sum the forces parallel to the surface, we have 53.4 to the right minus static friction to the left, and that should equal the mass of the object times the acceleration parallel to the surface. Again, this mass is at rest, so it's not accelerating, so the static friction force is 53.4 newtons rounded to two significant figures, because that's what number of sig figs we had in all of our given quantities, we should say 53 newtons.